Welcome to The Explainer. Okay, today we're diving into something literally mind-bending. We're looking at a revolutionary end-to-end smart agriculture blueprint that completely transforms traditional farming into a high-tech science. We're exploring the Agri Robot Design Challenge 2026, which outlines an entirely integrated ecosystem where artificial intelligence, robotics, and digital twins all work together to totally redefine how we grow, harvest, and distribute our food. Here's a quick roadmap for our farm-to-table journey today. We'll cover the Smart Farm Foundation, expanding to parallel ecosystems, precision harvest and quality, supply chain and sustainability, the digital nervous system, and finally, engineering the future. All right, let's get into it. Section 1, the Smart Farm Foundation. So picture this. We're completely tossing out traditional farming guesswork and replacing it with a fully AI-driven end-to-end ecosystem. By building a complete digital twin architecture, basically a perfect virtual replica of the farm, every single drop of water and every ounce of nutrient is optimized. It pushes crop health and yield prediction to absolute maximum efficiency. And this whole process kicks off before a single seed even sprouts. We're talking about three 3D spatial tiers of data collection. First up, the atmosphere, which is completely managed by drones. Second, the surface level, handled by smart irrigation bots. And third, the subsurface level, taken care of by specialized soil mapping bots. To put that all into perspective, up at the very top, drones act as these in-canopy microclimate sensors. They're reading temperature and light to actually predict plant diseases before they even happen. Then, down on the surface layer, canal bots calculate exact evapotranspiration rates, so literally not a single drop of water is wasted. And finally, down in the dirt, subsurface ground bots are mapping out this complex 3D spatial grid of soil nutrients. They're reading NPK levels and moisture spot by spot, allowing for highly variable rate application. Now, think about traditional farming. It relies heavily on broad-spectrum chemical spraying, right? Which, of course, leads to harmful runoff and environmental damage. Well, this new blueprint completely flips the script with a zero-chemical approach. Instead, it uses precision laser and high-voltage electrical weeding. Because, yeah, blasting weeds with lasers is absolutely not just science fiction anymore. So, in action, you've got these autonomous, solar-powered rovers operating entirely off the grid. Right alongside them, these robotic units are roaming the field, actively zapping weeds with those precision lasers and high-voltage electricity. It's totally chemical-free crop protection, working hand-in-hand with automated biospraying bots to guarantee absolutely zero harmful discharge goes into the environment. Section 2. Expanding to parallel ecosystems. But wait, it doesn't stop at plants. This specialized robotics technology seamlessly adapts for what we call parallel ecosystems. We're talking about smart livestock robots actively tracking the health of animals in the barn and specialized aquaculture bots constantly monitoring aquatic environments out on the water. These systems are constantly, and I mean constantly, tracking vital real-time metrics. They monitor animal temperatures, map out livestock behavior patterns, analyze aquaculture water quality, and even manage automated, nutritionally balanced feeding. By keeping this watchful 24/7 digital eye on all these metrics, the system drastically reduces feed waste and prevents devastating disease outbreaks across all of these parallel ecosystems. Section 3. Precision harvest and quality. Now we get to the really high-stakes part. To get the harvest exactly right, the ecosystem relies on a predictive AI copilot. Think of this as an advanced AI system that continuously crunches all that digital twin data we just talked about, specifically to pinpoint the absolute peak harvest day. It's a time-sensitive mission to capture what they call the extraction apex, basically the exact moment when ripeness and economic value are at their absolute highest. So the data node maps out this activation curve to target that precise extraction apex. But honestly, the real magic here is mechanical. A robotic harvesting arm uses AI vision to analyze ripeness on the fly and then applies mathematically calculated grip control to pluck the fruit without leaving a single bruise. It's incredibly delicate. Once that crop is picked, it enters the post-harvest quality gate. This is a seamless series of 3 completely automated stages. Stage 1, AI vision steps in for external flaw detection. Stage 2, a near-infrared spectroscopy, or NIRS, check ensures internal quality. And Stage 3, automated packaging. This whole gauntlet guarantees only the absolute best produce makes it off the farm. If we zoom in on that second stage, we are literally looking at the molecular level. That near scanner acts just like an X-ray. It peers right through the skin of the fruit to check its internal sweetness and sugar levels, all before it ever hits the automated packaging bots at the very end of the line. Pretty amazing, right? Section 4. Supply Chain and Sustainability. This is where seamless cold chain logistics come into play. Environmental data doesn't stop being tracked at the farm. It's monitored continuously from the farm, processing unit, right onto the transport trucks, and all the way to the consumer distribution center. It creates this unbroken chain of quality assurance, ensuring temperatures remain absolutely optimal for the entire trip. But let me ask you this. While the perfect fruit goes to the consumer, what happens to the massive amounts of biological waste left behind in the fields or nearby forests? If we're talking about a truly sustainable ecosystem, we absolutely cannot ignore that part of the equation. While the answer is the biomass and carbon loop, get this. A quadrupedal robotic dog acts as a forest explorer, mapping out resources and plant growth. Then, other bots step in to shred up the agricultural waste, and the system automatically calculates vital national carbon credits from that process. It is essentially a robot dog fetching economic value out of thin air. Section 5. The Digital Nervous System. We call this overarching brain the digital nervous system, and it handles 3 critical functions. First, a unified digital twin dashboard built on powerhouse platforms like SketchUp and NVIDIA Omniverse. Second, air-ground swarm coordination to direct all these robots. And third, autonomous tool swapping and docking, so the machines can actually maintain themselves. Through the hub tablet, the 3D digital twin processes everything in real time: soil, water, and energy. It perfectly coordinates the entire swarm of drones and rovers. Plus, it manages what they call endurance, where robots autonomously head back to swap out drill bits, sprayers, and batteries entirely on their own. It truly is a self-sustaining digital nervous system. Section 6. Engineering the Future. Now, as cool as this all is, machines don't build themselves. The core mission of the KU Agri Robot Design Challenge is to train a brand new generation of engineers. We need people capable of designing full-scale, sustainable precision agriculture systems that integrate everything, from the ground-level farm dirt all the way up to national carbon policy. Which brings me to a final thought for you. As farming rapidly evolves from manual labor into a highly integrated automated digital nervous system, what role will you play in engineering the sustainable future of food? I really hope this explainer gave you a powerful glimpse into what tomorrow's agriculture actually looks like. Keep learning, keep exploring, and I'll catch you on the next one.